Hello class, welcome to subtopic 3.7, trigonometric functions in terms of the unit circle. And this is the part 1 of maybe 3 or 4 because this is a little complicated. Okay, so let's see guys. Let's do a little backtrack and in order to define this new idea of the trigonometric functions in terms of the unit circle, this is the new concept, the unit circle. First, I need to walk you through the two previous things that we did in regards to trigonometric functions. If you remember, the first thing we did in order to define what a trigonometric function was the following. We said we spoke only of trigonometric functions in the context of the angles of right triangles. And what angles? Only these acute angles, either this one or this one. We never mentioned any trigonometric function in regards to this 90-degree angle. Never. Only these other two. And our definition was the following. If I have a right triangle, as specified by this mark, as you know, with sides A, B, and C, hypotenuse C, and if we have any specified angle in the triangle, let's say theta, then our definitions of sine of theta, cosine of theta, and tangent of theta are as following, right? Sine of theta is equal to B over C. In other words, opposite cathetus over hypotenuse. Cosine of theta was equal to adjacent side over the hypotenuse. And the tangent of theta was opposite cathetus over adjacent cathetus. And these are the first definitions that you know for trigonometric functions, but they only pertain to the acute angles of right triangles only. And we said that this definition was restrictive, right? Why? Because as we know, the angle of any right triangle, all of these three angles, either this or this or this, cannot be greater than 90 degrees. That's clear. Neither of these angles can be greater than 90 degrees. And so, considering only these definitions for trigonometric functions, we could never speak of something like this, sine of 105 degrees. This is forbidden in this context. It's meaningless. Okay, so we said, in mathematics, you have complete freedom of your definitions, and that's something very hard to understand at your age or at high school level. In mathematics, you are the creator. You can create your definitions. There are no constraints on that. There are no restrictions on what type of definitions you can create for whatever object. In this case, this object is called trigonometric functions, as long as those definitions are logical and consistent. Okay, you can define any object, any function, whatever, as long as your definition is consistent, as long as there are no logical flaws or voids. So as long as you keep that rule in mind, you can expand any definition you want, you can create any definition you want. So we said, okay, why don't we expand this first definition for trigonometric functions in order to encompass other types of angles? In this case, obtuse angles and even other types of angles, like, I don't know, 1000 degrees, etc. And we said the following. We define trigonometric functions of any angle in the following way. Suppose that we consider an angle theta of 120 degrees. Okay, and we said, how can I define the trigonometric functions of this particular angle? Well, what we did was the following, if you remember, and this is just a reminder for you. We said, let's draw this angle of 120 degrees in something that we called the standard position. And what that meant was drawing this angle with its vertex right here at the origin. Then the initial side, which I'm going to represent by an I, the initial side of the angle should be along the positive x-axis, and then you draw the angle in counterclockwise fashion. So 120 degrees, that would be all of this much approximately. It's 90 plus 30. And so this is my angle. This is the final side of the angle. So initial side of the angle, final side of the angle, vertex, and the rotation happens in counterclockwise form. So this is theta. And we said, okay, now having done this, my definitions for the trigonometric functions of this particular angle, sine of theta, cosine of theta, and tangent of theta, will be done in the following way. You're gonna pick any point along this final side, any point, it doesn't matter which one, any point. This point clearly has coordinates x comma y, and this point clearly has a distance from it to the center of my Cartesian plane, or the vertex, right, which we called r. This little part in here we called r. And the definitions of sine of theta, cosine of theta, and tangent of theta are ready to be specified. We said sine of theta is going to be equal to the y-coordinate of that point over the distance r from the point to the origin. Cosine of theta is going to be equal to x over r, and tangent of theta will be equal to y over x. These are my definitions for these trigonometric functions of any angle whatsoever. So this is a more open definition because now it allows me to calculate these objects, trigonometric functions, for this particular angle and any other type of angle, not just angles less than 90 degrees. And we said that this definition, in particular, this second definition, actually takes into account the first one when we stick our study to the first quadrant. Okay, when we draw the angles only in this first quadrant, for example, this other angle, which I may call alpha, then when I do that, when I study these trigonometric functions only in this first quadrant, basically what I'm doing is getting the trigonometric functions of the angles of right triangles, because I would be forming, when I get that point in this final side, I'm gonna be drawing this, right? And basically I'm gonna be doing the same I was doing here. So this is a more general or broad definition. Okay, and those were the two things that we have done in regards to this concept of trigonometric functions. Okay, now let's do a little more, guys. It's gonna be something very similar to the second idea, which is the following: the trigonometric functions in terms of the unit circle. So first, let me tell you what the unit circle is. It's a very simple idea. The unit circle is a circle that lives on a Cartesian plane and whose radius is equal to 1. So basically, if I draw these little marks, this is 1, this is minus 1, minus 1, and 1. These are the intersections of these cuts along those axes. No, this is not minus 1, this is 1. This is minus 1, this is 1. Okay, then if I draw a circle throughout these 4 marks in this way, as you can see, this circle has a radius of 1. You see, because the distance or the length from this point, from this origin, to any point in the circle, in this circumference, is 1. The radius of this circle is 1. Okay, that is what the unit circle is. It's just a circle with the radius equals 1. It's that simple, guys. Okay, now I'm gonna be basically doing the same I did in here in order to define the trigonometric functions of an angle theta in general. And just as a disclaimer, guys, for this definition, for this third definition, we're gonna be considering angles, in radians, always in radians now, not degrees but radians. Okay, so how does this work? Same thing that we did in here. We're gonna, if I have an angle theta and I want to calculate, or if I want to define these three objects known as sine of theta, cosine of theta, and tangent of theta, these three functions, what we do is this. We're gonna draw the angle in standard position. I already explained to you one more time what a standard position was. So this is the initial side, and then let's draw theta. There you go. This is theta. And as we can see, the final side of theta will cut the unit circle at this point, which, just like before, has to have some coordinates, x, comma, y. All right. And now the good thing about using the unit circle, guys, is that the distance from this point to the origin, if you notice, it's the same as the radius of this circle. And I already told you that the radius is equal to 1 by definition. That's why it's called the unit circle. The radius is 1. So let's write that in there. And basically, guys, the definitions are the same as in here. Sine of theta for this particular angle will be its y coordinate over its distance from the point to the origin, which is 1. You see? And so basically it boils down to just y. Sine of theta is just y, which is the y coordinate of the point of intersection. You see that the final side of the angle theta, the intersection that it makes with the unit circle, it's just this number. So the whole idea is to simplify this definition into this other. Instead of having now y over r, we just have y, because it so happens that in this context for the unit circle, my r, which was the distance from the point to the origin, my r will always be 1, and that simplifies matters a lot. So sine of theta is simply y, which is the y coordinate of this point. The same is going to happen for cosine of theta. Cosine of theta is the x coordinate over the distance from the point to the origin, which is 1, and that boils down to just x. You see? And finally, tangent of theta is the same as before, is the division of the coordinate y over the coordinate x. There you go. So what is why do we need to define these trigonometric functions now in terms of the unit circle? Because one of the reasons is that it makes the functions look cleaner. It's just sine of theta will just be y, not y over r. You see, we have no denominators like in here. It's just y. So it's a cleaner version of these functions. It's just, let me erase this thing. Sine of theta will just be doing this. You have the unit circle. You draw your angle theta in a standard position. That angle theta has a final side, which is this in this case. That final side cuts a point or intercepts a point along the unit circle. That point has two coordinates, x, comma, y, as any other point. And basically, sine of theta will be equal to the y coordinate of such point. You see, it's a much simpler version than this one. And the same for cosine of theta. Cosine of theta is just the x coordinate of this point of interception between the final side of theta and the unit circle. You see, it's a simpler version of this previous idea. And I'm gonna stop it right there. I'm gonna stop it right there. Okay.